This conference will now be recorded.
Thermal comfort as a state of mind that expresses satisfaction with the thermal surrounding. Before lunch, we discussed. Here now we are talking about influencing factors about activity, that is metabolic rate, clothing, air temperature, mean radiant temperature, air movement, and humidity. So, as we were discussing also, can we have any index created out of activity, absolute humidity and temperature or RH or something? So probably all these 6 parameters need to be combined together to arrive at the thermal comfort. See, defining thermal discomfort could be a little easier, and these are the indications of thermal discomfort displayed by working people at their respective offices. All these are what? They are indications of direct draft hitting them, which is probably more than the acceptable range of what we saw of 0.15 to 0.5 meter per second velocity, or it could be too cold or something. But so people have taken pains to maybe climb up a ladder or a stool or press the this thing grill, or somebody have even put plastic or papers inside the grill itself to stop that this thing. People have stopped the this thing or closed the grill entirely as well. So, and this is the another picture of thermal discomfort where you can see this gentleman on the top left hand corner in his cabin. He is sitting in one place, but on the supply and return grill on the opposite side. So he would never get a direct draft or cooling something. So he has adjusted or arranged for a pedestal fan. Similarly, in this office, you can see supply grills have been provided here on the periphery. Here also other side it would be, but still you can see about 3 split AC units. Here you can see again some grills are there, but people have also arranged for pedestal fan for themselves so that they can be comfortably working or this thing. So these kind of indications are where people show their dissatisfaction or they feel uncomfortable situation by either there is too much of air movement or too less of air movement. Temperature and relative humidity would play, and these are then here we are normally discussing with the normal clothing what Indian people would wear to office or work, and this thing. So you can see a nice comfortable looking office, but actually it is not. So now when we look at ECBC with this background of thermal comfort and what AHU would do or things would make to work. So I have chosen this hot and dry and warm and humid climate, which are again represented mainly throughout the Kerala. And as we saw, first thing we need to work on the good quality envelope, and then we need to improve the active controls and system, and then put the additional. So if we do as a package one or the initial set of actions as a window, wall and roof measures as a first activity, then all these can result into 21% saving, but the payback would be 8 years alone for all these civil measures. But then if we look at cooling packaging and other lighting efficiency and everything, then by improving controls and having a good cooling strategy, including some passive measures as well as some active control, the savings would be increasing to about 29% from 21%, so additional 8% saving, and the payback would lower from 8 years to less than 6 years. And if you put lighting measures and final controls, everything, the savings would jump from 29% to 36% overall, and payback would be about just 5.5 to 6 years. So this was coming out to be from a study of the White Group and Sept University that done an extensive survey of existing buildings as well as implemented ECBC implemented buildings, and they have found out if these kind of measures are done or redone for an existing building, then things can improve. See, in fact, some of the glass manufacturing companies, they also offer to change your facade. Maybe even if outside facade changes are not possible, then they retrofit it from inside to the existing facade with a DGU as well. So people means so products and services are being evolved and offered to even make these changes. Lighting retrofit and changing is now no more a brainer, and probably everybody has done that in all their offices or new projects are implementing. Anything doing for the facade or for the envelope is little costlier and tricky, but people have been able to do that as well. So as a part of construction and permitting process of ECBC compliant projects, the urban local body approval would be at the design stage. Then during construction of the opaque envelope or something, completion and occupancy certificate would be get. And then either owner, tenant, or based on whosoever is occupying that building, HVAC, lighting and other controls would be put in place. So these are these packages which we can look at how they would mean. So now, apart from all steps of ECBC compliance, right from envelope, HVAC, service, hot water, lighting, and electrical power, today we would concentrate on HVAC, which is our main area of discussion today. So for compliance approaches, we need to meet mandatory provisions of section 4 to 8. And then for balance of some low performance components or with higher performance component, for envelope only there is a trade-off option available, and then depending on what size of project and how complicated that could be, either prescriptive approach or whole building performance method is arrived at or used. So in HVAC, heating, ventilation, that is natural and mechanical ventilation, and air conditioning, that is cooling, dehumidification and humidification is included. Again, HVAC word or this entire artificial air conditioning has originated in the Europe or North America. Heating, which I have mentioned, is predominant for more than 7 or 8 months in a year. So heating becomes their main contention. Then ventilation, and then air conditioning, which could be cooling, dehumidification or something, which could be just about 3 to 4 months in a year. So to meet these requirements, they had worked. So heat load sheet also occupy. So now we are dealing with various clauses and requirements of this thing. So for thermal comfort, temperature, humidity, and indoor air quality, which is availability of good amount of fresh air continuously, which is filtered and supplied, is required. Then external factors responsible are heat, solar gain, outside air, which could be hot and humid, and the conduction of heat through the envelope is there. And then the internal loads would be people, equipment, and lighting. So all our computers, then maybe data servers or even printers, everything, whatever, even the hot water kettles, etc., are equipments which add to finally heat to the surrounding because they are part of the air conditioned area. And lighting. So heat exchange with surrounding happens as a product of this thing, addition or subtraction of metabolic rate, convection, net radiation, conduction, evaporative heat loss, and change in heat stored. If delta S is positive, then the heat stored would be also the work would be done by the person, or if it is negative, it decreases, and people need to deal with these changes. Psychrometric chart we saw, which talks about wet bulb temperature, dew point temperature, absolute humidity, that is the absolute moisture content of the air, humidity ratio, vapor pressure, and relative humidity, that is the percentage saturation as a part of this thing. Now here we will be talking about one of the most widely used air conditioning system in the world is water cooled air conditioning system, which is a package chiller is there. So that chiller comprises of a compressor which compresses the refrigerant into a high pressure, high temperature vapor. Then there is a water cooled condenser which transfer the latent heat of condensation to water, and it goes and it discharges at cooling tower. And then the high pressure, high temperature liquid. So here high pressure and high temperature vapor is converted into high pressure, high temperature liquid. So pressure and temperature doesn't change. Only there is a phase change from vapor to liquid, and that latent heat of condensation is rejected at condenser. There is nothing else. Then there is an expansion wall which would suddenly expand that high pressure, high temperature liquid into a low pressure, low temperature liquid. Then there would be an evaporator which would again, after the work is done, low pressure, low temperature vapor is going will be sent back to compressor. So this is a package chiller comprises of compressor, condenser, expansion wall, and evaporator. Now let's look at the condenser cycle. So this hot water at the outlet of this condenser is then that heat is rejected in the cooling tower and heat is let out. Then that cool water means it will be about 3 to 5 degrees centigrade above the ambient wet bulb temperature. The water will be cooled to. Then through a condenser transfer pump, it would be sent back to the condenser for again extracting the heat. So this is how the condenser cycle would work. Now let's look at the user end or the evaporator cycle. There is a primary pump which takes back the hot liquid. So here in the condenser cycle, when we talk about hot water or cool water, we talk about water coming at 36 or 37 degrees centigrade and getting cooled at 32 degrees centigrade. Or typically, I'm just giving these numbers, which would be probably would be you can get that water temperature of 32 degree very easily in Kerala, all parts during at least monsoon and summer months. In winter that temperature can go little lower as well. And here when I say for evaporator circuit hot water, the hot water is 12 degrees centigrade because my cold water through a secondary pump is supplied to the user area at 7 degrees centigrade through a secondary pump. Then from that secondary pump, that water goes to various AHU coils, and that coil will supply that cool air to about 14 or 15 degrees centigrade, which I saw just one slide before lunch, to the user area, and then that hot water at 12 degree will come back to evaporator. So evaporator cycle essentially will operate at 712 cycle if they need to remove the latent load or the water vapor. So the dew point of air is achieved and air is let out at about 13 or 14 degrees centigrade and 95 to 98% RH. This thing, and it mixes with the 24 degree and 50% RH or 55% RH room air, and this rate of heat infusion into an AHU and room office area is usually the same rate at which heat is being added to the room by people and systems. So all internal loads are taken care as well as external heat gains. So this is the entire cycle of a water cooled system. If we are dealing with air cooled system, then cooling tower and condenser pump is replaced by a fan which will extract that heat from ambient. So ambient air, it will try and suck and pass over the condenser coils, which are copper tube fins, this thing, and it would reject that heat to atmosphere. Now in this cooling water or condenser cycle, the water temperature would be about 3 to 5 degree above the wet bulb temperature of the water, because here water is the heat exchange media with the air. But in case of air cooled system, it will be probably 5 to 7 degrees above the dry bulb temperature of ambient air. So even though we are talking about coastal areas of Kerala, there could be a 4 or 5 degree difference between the dry bulb and wet bulb temperatures, unless otherwise monsoon. In monsoon, it would be raining. So while raining, it will be at 100% saturation line. So your dry bulb and wet bulb will be coinciding. But at all other times, even at very high humidity, 80% humidity or relative humidity, your dry bulb will be tend to be little higher than wet bulb. So that means our condensing temperature and pressure of refrigerant using air cooled system will always be higher, and that is why air cooled systems are always little inefficient than the water cooled system. So the energy consumed by compressor in air cooled system and avoided cost of cooling tower, cooling condenser pump and cooling tower fan in water cooled system, you will get a little higher condensing temperature and pressure of your refrigerant cycle, and so compressor will consume little more power. So compressor power consumed versus the cooling tower means the air cooled condenser fan power always will have an higher output or product versus your water cooled system. So that is where water cooled system is more popular and more efficient. So when we will see COP values or other values as a comparison, we will notice. These are the old reciprocating compressors, and ECBC does not allow or recommend or talk about these efficiencies, because whatever efficiencies now ECBC is talking about, these values are not being met by these old compressors. So these are the reciprocating compressors are retrofitted by the other chiller circuits, etc., which are also even seen today in many industries or services. And this is what you are talking about, a modern chiller unit, where all your motor, condenser, evaporator, and compressor, including expansion valve, are packaged and standing on one single platform or this thing, and then you have various connections for all these heat exchangers. So this is your screw chillers with the screw compressor and motor, which are insulated in the housing on the top. Then there's nitrile rubber insulated evaporator, and then below you have a water cooled condenser. And this is how modern chiller plant room looks like. And this is Mindwell photo is from India itself. It is from Mumbai, one of our clients' plant room. So on the right hand side here, you can see these water cooled chillers, multiple 5 number chillers they have installed, and here you can see primary and secondary chilled water pumps being installed here on this line. This green line is a cooling water line, and all these white insulated lines are the chilled water lines. So for 5 chillers you have 5 primary pumps, and for zones they have 8 secondary pumps operating, and then electrical panel is in between with a proper arrangement. So this is how a good system, HVAC system plant room looks like. And when we compare efficiency of a plant room in ECBC, ECBC plus or a super ECBC building, all these equipments are part of that. And this is an air cooled VRV system installed at a rooftop. And if you can see now, there are these exhaust fan and the fin tube. So these fans allow air to be drawn from all 4 sides, and heat is rejected to the top. And again, you can see they are out in the hot sun, and for waterproofing purpose some tar has been applied, tar sheets have been applied on the terrace, so entire surface and things are quite hot, so adding to little inefficiency of the system. So in the HVAC system, when we talk section 5.2 of this thing for a building, and here it talks about energy efficiency, then whole building design approach, where mandatory requirements are section 5.2 for ventilation, then equipment efficiencies are stated in 5.2.2.1, then controls are 5.2.4, and piping ductwork 5.2.7, system balancing is 5.2.8, and condensers are 5.2.9. And then there are prescriptive requirements for fan, pump, cooling tower, economizer, variable flow hydronic system, and heat recovery system, which are from 5.3.1 to 5.3.6, which need to be followed for demonstrating compliances. So here you can see there are so many systems and equipments which would require for an optimum or efficient performance of a system, and not just IKW or IPLV value of chiller alone is responsible for overall efficiency. So first control is timer clock for mechanical cooling and heating systems in office, mall, etc., where the built-up area is more than 15,000 square meter. It's a 24-hour scheduling can be done for loss of power of retention of program, and it should have a for cooling systems which are less than 17.5 kilowatt. That is about 5 TR system, and a heating load of 5 kilowatt, that is 1.5 ton system. Timer clocks are not required unless otherwise there is a process requirement. Like say typically even smaller data hubs or the server rooms, which are not data center but the server rooms, they would have typically 1.5 to 2 ton two machines installed, one operating, one standby in a cyclic mode. So every 2 hour or 3 hour, depending on the cycle timer set, each machine would start and stop to gain that control. Then the second set of control 5.2.4.2 is temperature controls for mechanical cooling and heating for all offices more than 20,000 square meter. And it should have capabilities of providing temperature dead band of 3 degrees centigrade. So if you have a simultaneous heating and cooling possible through a single machine, that dead band has to be there so that there is no overlap or cross signal going from one sensor. Simultaneously there could be a one sensor or signal would be asking for cooling to be start, and the other sensor could mislead to a heating to be start. So that 3 degrees centigrade clear dead band is required. Then for warm and humid climates, RH should be controlled or should be below 60% at all times, and thermostat will be used for controlling RH as well as temperature. And also for hotel guest rooms of less than 25 square meter or 250 square feet should have these requirements. Then there are occupancy controls required to de-energize system when not occupied, non-regularly occupied spaces, then hotel guest rooms, restrooms, pantries, photocopier room, etc. need to have sorry, these kind of controls. Sorry. Then fan controls are there for cooling tower and closed circuit coolers with a built-up area of more than 20,000 square meter. Either it should have a 2-speed motor or it should have VFD. Then the control should be capable to reduce fan speed at least to the 2/3 of installed fan power. Then there need to be dampers on air supply and exhaust equipment, and damper shall be closed upon when the fan shut down and the spaces served are not used. So by default, these dampers will be in closed position when the system is not functional, and when the fan is switched on, sensing the draft pressure, the damper will open, or there could be a solenoid or actuator signal which will open the automated. Additionally now, so here these controls we were talking about only in the ECBC compliant building, but ECBC plus and super ECBC buildings of similar size would also require centralized demand shed controls with the BMS or DDC zone level control. It should also have a demand response control, then always have manual override facility, then supplier reset temperature with respect to building load or outside air temperature. It can be reset for 25% of air to be at saturation. So that means when you have a large building of say 2 lakh square feet of built up area, that means typically a chiller load of about what it could be about 200 tons of air conditioning. to 150 tons of air conditioning, these buildings would have these BMS and DDC controls, and also provision of chilled water temperature reset based on the written air temperature as well as from the system when the ambient conditions are quite cool. So maybe in a place like Munnar in Kerala, it's a hill station. So in winter months when the temperature drops down, or during daytime also, instead of operating your chiller at 7 degrees supply chilled water temperature, you can increase your supply chilled water temperature to about 8 degree or 8.5 degree based on the written water temperature and control your system. Let me tell you something, operating chiller at higher temperature always gives you much more saving than controlling your AHU fan power or pump power. Because compressor has the largest motor, so typically 100 TR machine will have about 75 kilowatt of motor, and which will be operating or consuming about 55 to 60 kilowatt of power, typically at 0.59 or zero point 0.6 kilowatt per TR. And then the corresponding pump power could be 11 kilowatt, or AHU fan could be about 5.5 kilowatt each, kind of thing. So trying to save everything on the controls on the other side or user side, it could be much better to control your chilled water supply temperature first based on the feedback received, which could be, and then also it can be ramped up or down very easily if you have VFD in control. So for super ECBC buildings, your area, variable air volume fan control. So fans in VAV system have controls for fan motor or no more than 30% of the load or design wattage and 50% of design airflow, when the static pressure is 1/3 of the total design pressure. So that means when system is at less load, typically early in the morning in an office or end of the day in the office when only few people are working and maybe few cabins or few cubicles are occupied, and maybe 70% or 60% people have already gone home. So then for that balance 1/3 load, and even ambient conditions could be little favorable because probably there is already a sunset happened or is about to happen. So with that, my based on my VAV box feedback coming, my AHU fan should modulate, as well as it should also show me how much it should be still able to uh, comfort and control the temperature and RH to the farthest cabin or the sitting area inside the office. Air side economizers are not again meant for warm and humid climate, because we will very rarely have 14-degree or 15-degree air temperature during daytime, and for anything less than 200 or 300 such hours in the year in the working office hours of that system, it may not be worthwhile. Maybe at some hotel in a hill station in Nilgiris or Munnar, this could be as also done when ambient is at 40 degrees or something. You can just take that air directly from outside, filter it and pass it through the rooms instead of running all your chilled water pump, chiller and AHUs, etc. Then it should be also capable of automatically reducing outdoor air intake to the design minimum value, or override it and give a signal for chiller supply. So now if we compare older ECBC of 2007 versus ECBC 2016-17, then the natural ventilation was just a mention there. But here in the new ECBC, we have natural ventilation, air quantity design requirements, mechanical ventilation requirements, operational control for minimum outdoor air, demand control ventilation, all are included as an added this thing. Similarly, for chillers, minimum equipment efficiencies are there. Then controls where same controls we are talking about even today, but that's a different section. And a new section has been added of 5.2.3, which is talking about minimum equipment efficiencies for all chillers, pumps, cooling towers, fans, etc. Then piping and ductwork. So even 5.2.5 is we have additional control for ECBC plus and super ECBC buildings. That is for central demand shade control and supplier temperature reset, chilled water supply, etc. And then we have VAB fan control, air side economizer controls. Then condensers, and we have piping system. Then additionally we have system balancing. And then for condensers, we have treated water and other requirements have been also added. Additionally, there are prescriptive requirements, and then fan, pump, cooling tower, economizer, variable flow hydronic system, boiler, low energy comfort systems, and heat recovery, which has been added to the new ECBC. So how to do that? First is again reduce the load, just quickly recapping, then meet loads efficiently and use clean energy. You have to be lean, half the demand, then mean by doubling the efficiency, and then you can be green or efficient. So check your assumptions, start with need or service in mind, not the amount of stuff required to provide it. Reduce the loads that cause the need to the service first using passive means. Select appropriate system types designed for elegance. Then use efficient equipments. So it is also mentioned most people start here. No, we should not look at efficient equipment first. We should speak about reducing load first, and how good or bad or how realistic our assumptions and requirements are. Then that to question to the client and then meet these requirements. Then switching off when not needed by controlling. So that is another way of doing. Then examine all waste streams which can be used by other systems functions. In fact, we know a hospital which takes out that hot cooling water. They are circulating through a coil by a means of plated exchanger for controlling RH to the critical areas of ICUs and operation theaters. So heat rejected cooling tower with that water would be at say 36 degrees centigrade or so is moved again through a separate coil in the AHU. So you have a 6-row deep cooling coil, and then you have 2-row deep hot water coil. So cool dehumidified air is again reheated and humidity is controlled and then sent to the OT or ICU critical area. But then using that hot water again from your cooling water circuit through a PHE. So that dirty cooling water does not come in contact with your AHU coil, and there is no puncture or there is no other risk. So it is all done at plant room level. And but then that secondary chilled water, which is that 28 or 29 degrees centigrade, is good enough for passing. So that hot water is not literally a hot water. It is that water is usually available at about 28 to 29 degrees centigrade. Then count all benefits and cost upstream, downstream. Then look at the life cycle cost analysis and use. So now in ECBC, we have always been talking about meeting U values or something or insulation. So if we are just doing a 230 mm clay brick, the U value of that clay bricks 230 mm with plastered from both sides would be about 2.03 watt per hour or per meter square per degree Kelvin. But if you use a aerated autoclave concrete block or AAC block, that U value is 0.7 watt per meter square hour degree Kelvin, which is about reduction in heat gain by 61%. If you use brickbat Coba and 150 mm slab concrete slab as standard roof, then the heat gain by the roof is 3.92 watt per meter square hour degree Kelvin. But if you add 2 inch of EPS, XUS or PI or PUC, any kind of artificial insulation, then it reduces U value by 2.33 watt per meter square hour degree Kelvin, which is almost like 92% saving in the testing. Same way glazing, you can have single glazing and solar heat gain coefficient of 0.67 and U value will be 5.7. But if you go for a double glazing, then your SHGC will be less than 0.3 including frames, and U value could be 1.7. So all these things you can do it. So this is probably easier way. Okay, you use these methods. So this is how prescribed method would work. If you simply choose these kind of AAC block or roof insulation or DGU, mostly you will meet ECBC requirement without much of a botheration. Sorry. So any climate zone which does not have any season for more than 6 months will be called as a composite zone. So in the composite climate, you have higher means winter is harsh, summers are also harsh, and there is more than 1100 millimeter of rainfall or something. So all three seasons are distinctly seen. But like in coastal cities in Kerala or in Maharashtra or in part of Chennai, Tamil Nadu, Kolkata, all that coastal areas, you will find our summer is predominant and monsoon and summer temperatures, humidities don't vary much. And we have negligible or very mild winter. So we have warm and humid climate, and temperatures are normally about 30 degrees centigrade, and RH is also more than 55. Or the other day when it rains, temperature would be still about 25 degree and RH would be more than 75. But temperate and hot and dry climate, you will have other good seasons available. And in NBC again, which is also parallel document to be referred for all design requirements and compliances of statutory or voluntary nature, would be for the part 8 section 1 2 3 4 5 6 for all these lighting, electrical, light insulation, air conditioning, acoustic, live escalators, and other information. This thing. So in ECBC, this thing they talked about building orientation, inlet opening, outlet opening, height of the openings, and total area of the opening. So here the for the offices, your height of opening should be about 0.75 meter from the finished floor level. If sitting on a bed for a bedroom, it could be zero 0.6, and sitting on floor or the low sitting area, it could be 0.4 meter. The inlet opening should be on the windward side and the outlet opening should be on the leeward side. But typically in the west coast of India, in Kerala to Mumbai, we will have our predominant wind direction would be south-southwest. So all those openings, if we keep smaller and have larger openings on the north side, then most of the heat will go. And again from north side, we will get all glare-free light without much of heat. So leeward side, you will have say probably 2 times or 3 times bigger size of window opening, which will serve two purposes. We will get all glare free and more light without heat, as well as it would create a good negative pressure and would invite more air to come for the natural ventilation. But along with that, there could be a more humidity will also come inside, which we need to take care of. So in natural ventilation, have permanent roof or wall openings in windows, doors, and louvers to outdoors. Openable area should be 5% of floor area for the naturally ventilated space, and should be between 14 feet of roof or wall opening, and have minimum 3-star rated ceiling fans. So these are the requirements mentioned. In the hotel, motel, guest rooms, etc., open to and within 8 meters of operable roofs, to it should be provided. So this is a 28-watt BLDC fan, and mechanical ventilation is again shown in BC, where optimum room size versus room length and width, you have how many fans you would need. Then temperature rise and air speed. So limits for light, primarily very sedentary activity like office activity or something, your temperature rise in Fahrenheit should be not more than 6 degree Fahrenheit with the air speed of around 160 feet per minute, and average air speed in meter per second could be in the range of 0.9 to again 2 degrees centigrade. Naturally ventilated, this is what I was mentioning about indoor operative temperature. So in naturally ventilated buildings, you have a multiplication factor of 0.54 into outdoor temperature plus 12.83 as a constant. So indoor temperature is neutral and outdoor is 30-day outdoor running mean air temperature. If you look at it as our from our climatic data, we can find out these values. So 0.54 into 33 degrees centigrade plus 12.83. So when we have an ambient condition at 33 for a naturally ventilated building, if my indoor temperature is 30.68, it should still be very well acceptable number. Then in an air conditioned building, as I mentioned, when ambient is at 45 degree and indoor, if you want to maintain 24, it could be little disastrous for the users because they can experience thermal shocks. So the multiplication factor is 0.078 and plus the constant is 23.25. So again for a 33 degree ambient temperature, your indoor operating temperature would be close to 25.8 degrees centigrade. So this we can check and vary. Then fresh air, how much fresh air we should provide. So there are two ways of providing fresh air. So 5 CFM per person in an office space plus 0.06 CFM per square foot has to be provided. That means in especially most of us would have experienced this in the hotel rooms or something. If there we just enter, if that room was not used for many days, we will find some peculiar smell of the stale air in that room. So in that case, when there was no guest, minimum 0.06 CFM of fresh air per square foot of area. So suppose you have a 100 square feet guest room. So 0.06 into 100, 6 CFM of fresh air should have always been on in that guest room to take care of all those smells, etc. So there is enough extraction of heat as well as mold or other this thing in the room. So even there is no person in that room, this minimum ventilation has to be maintained. And when you go for places like cafeteria or retail sales or malls, etc., or banks, where we will have typically more density of people in smaller areas, then your air quantity minimum CFM per person goes up to 7.5 CFM, and the CFM per square foot varies from 0.1 to 2.18 this thing. So in cafeteria, naturally it is higher because there would be a lot of food preparation and other smells which also need to go away. But in the banks or something, you will have higher people density, but then CFM per square foot could be 0.06. So it's an addition of both these numbers. It is not just one number in isolation. But it is exception is there for the places spaces with demand control ventilation, and average rate of occupancy is varying. Then ECBC also talk about low energy comfort systems where evaporative cooling, desiccant based cooling systems, solar air conditioning, tri-generation, that is waste to heat and power, radiant cooling, ground source heat pumps, adiabatic cooling system, etc. So these are technologies which have been accepted as a proven low thermal comfort energy systems, and all these efficiencies, etc., need to be maintained for the piping, ductwork, and system balancing. So when we talk about radiant cooling system of certain capacity for a larger building, it would have a higher capital cost, but the payback would come in less than 3 years. Instead of cool air being circulated through air conditioning, it would circulate cold water. So the amount of or the size of air duct will get reduced by the size of chilled water pipe. Then large volume of air displacement needed for comfort, and air exchanges restricted to fresh air requirement. Large fans are required to move the air, but small pumps are required to move the water. Higher speed to volume ratio can cause noise, but the water pumping would be in some corner in the basement or at the ground level or in terrace, and it will not cause any humming sound or disturbing sound. Thermal comfort in the radiant cooling is very high, and MRT achieved is also much lower and better. So this is how an radiant cooling in office would work, and these kind of sheets are then used in these office areas and then through these orange colored pipes coupled, there is a flow of chilled water through this system. So this is the schematic of radiant cooling system providing this thing. So you have a DOS is a direct outdoor air system, which will be ventilation air. So 100% fresh air as well as higher chilled water supply temperature it can provide. So if you install a PHE in between, so for your air conditioning, humidity control, you will use that chilled water. But then you will also use a pump with a plate heat exchanger where the chilled water for radiant cooling would be supplied at 1619 circuit, which would reduce your cost of energy for pumping. So your kilowatt per ton value for generating chilled water at 16 degrees will be hardly 0.25 or 0.27 kilowatt per TR as compared to 0.6 or 0.55 kilowatt per TR for a 712 circuit. The heat capacity of air versus heat capacity of a cup of water is same. This is how we are trying to show. So 3/4 HP fan would deliver 1000 CFM and through a 20-inch duct, whereas 2 GPM water can go. So pumping cost is 7.5 times less when you are using water. Demand control ventilation for conference room, meeting rooms, or areas which are not regularly occupied. So by having motorized dampers and room sensors for the temperature, this thing, you can have a demand control ventilation based on the temperature, written temperature, RH and CO2 levels. This pressure can be then supplied through a centralized system. So all classrooms, call centers, or continuously occupied offices, healthcare, and public areas are exempted from this demand control ventilation. And spaces which are less than 150 square feet or 15 meters square are also exempted from this. Design occupancy of less than 10 people does not also call for a demand control ventilation. The terminology is what we use in air conditioning is coefficient of performance, which is the COP, that is rate of heat removal versus rate of energy input, and again COP, rate of heat delivered versus rate of energy input. Energy efficiency ratio is rate of net cooling capacity in terms of BTU per hour divided by rate of electrical input in watts. So on all our 5-star or 3-star, 4-star window split AC units, you will find it has been mentioned in ER. So 1 BTU is 1 TR is 12,000 BTU. So 12,000 divided by say input is should be say 1 kilowatt or 1000 watts. So it would be 12,000 divided by 1000. So ER will be 12 like this. So integrated part load value is a single number figure on merit of part load, which will be combination of ER, COP or kilowatt per TR. So 1 TR is 3024 kilocalorie per hour or 12,000 BTU or 3.516 kilowatt. Or 1 kilowatt of refrigeration is 0.284 TR, or it could be 1.34 HP, or it could be 3412 BTU per hour. This is an air handling unit looks like, where you have a cooling coil and fan motor assembly mounted on a skid. Otherwise, smaller units are same units but of much smaller capacity, which are hung at the ceiling as a ceiling suspended unit, orange colors one. This is a heat recovery wheel. So outgoing cool air through maybe toilet ducts or some a dedicated exhaust can be used because that air would go out at say 24 degree or 25 degree centigrade and 55 to 60% RH. So that can cool 35 degree and 60-70% RH air by at least 2 or 3 degrees centigrade. So that much load on our main system then can get reduced. So these energy recovery wheels also can be used on split AC units as well, where you can have a dedicated pressure fan or a system. So air being coming in, so the same amount of air has to be exhausted. So on that, we can have a smaller energy recovery wheel installed. So in the ECBC, there is a provision, the air cooled chiller minimum COP we are talking about 2.9 to 3.05. But the moment we come to or IPLV value of 3.16 or 3.32. But when we come to water cooled chillers, immediately we talk about COP value of 5.8, 6.3, etc. and IPLV value of 6.09 to 6.61. Reciprocating compressors are water cooled are again 4.2 to 5.05, but they are now rarely being used, or rather not used at all. Rotary screw and scroll compressors, again they are smaller compressors used in VRV or other the standalone package systems, but again they are little efficient and air cooled system, but not so efficient as water cooled systems. So there is a misnomer or conception which calls for says okay, water cooled means VRV is more efficient. Yes, it can be more efficient at part load, but as compared to air cooled machine, but not a water cooled machine. Mithun has asked, can you share CFM per person figure in hospital? Again, CFM per person in hospital in a patient room would be about same 6 CFM or 5 CFM per person, but the number of CFM per square foot could be 0.12. If it is a ICU kind of a contaminated area, then your system requirements or medical facility requirement governs the CFM per square foot of fresh air, which usually could be one air change or more than one air change per hour of fresh air, or two air changes per hour kind of as well. Some of the COVID facilities we had designed in ICU, there we are directly taking 100% fresh air once through. So there is no recirculation. But for normal ICUs or something, depending on what kind of criticality of that ICU, we can always pick and choose the air quantity. So it is governed by which kind of contaminants or this thing. See, if it is a normal orthopedic hospital ICU, then there will be less chances of any infection or something. There would be, I'm sure, but then comparatively less. But if you have a ICU for say kidney patients or for heart transplant patients or something, then those are much, or even brain surgery, then those are much more critical areas where you need a lot of fresh air to be governed, and then that is not usually in terms of CFM per person, but that would be in terms of number of air changes, and usually 1 to 5 or 6 air changes can also be delivered depending on the contagious infection. If you have wards of TB patients or others, then you will never use that air back in the system. So it will again depend. So hospitals again are not the usual ones, but then your medical facility team will decide, or doctor would say how many air changes they want, and that we will have to provide as an HVAC consultant. Then minimum efficiency for ECBC, ECBC plus and super ECBC buildings, we have these numbers coming. So in super ECBC building, you can't use air cooled chillers, period. So they are very clear about in which building what kind of system would go. So if you want your building to be exceptionally air conditioned, you will have to go with water cooled chillers. And now look at for water cooled chiller COP values also how much they are varying. So for a constant speed up to 150 TR, it would be 5.5 COP versus ECBC plus it will have 5.8, and in super ECBC the COP value is 6.1. So for a larger capacity chiller, say like 600 TR or more, you will have 6.1 COP, 6.5 COP, and 6.7 COP. So all these numbers in Super ECBC or ECBC Plus will be on higher side. Again, cooling capacity of water cooled for unitary package. These are smaller or package systems than Super ECBC and this thing. So they will also have a higher amount of efficiency provided for air cooled as well as water cooled. For VRV, again, this is a new section which has been introduced in new ECBC, where system minimum COP efficiency value is 3.28 to 3.02. So for a smaller size, this thing, 3.28 COP, and if you compare this with your even air cooled chiller efficiency, VRV has a less efficiency. Even it is little inefficient as compared to package units as well. So people talk about VRV being very efficient. They are only effective when system is operating on part load or if the load is variable. See, like if you go to a multi specialty clinic of doctors, so where doctors and patients would keep on coming and going at some pre-appointed hours, and always it will not be occupied, or it could be less occupied in certain hours or something. In that case, go for a VRV. But if you have a constant load like in office, everybody comes at 9 o'clock and leaves by 6 o'clock or something, VRV is of no use, because your ambient conditions in Kerala are almost constant. Inside load is also going to be constant. Then there is no variability, so VRV is not going to help you. VRV will help us only when we have part load conditions for significant amount of time. If 30 to 40% times or even more, if my system is going to go between peak and off peak loading, then I should select a VRV. But if everybody comes to office and everybody goes in the evening, so daytime there is hardly any change in the occupancy or something, or there are no visitor floating population, VRV is not for that system. It's only a marketing or this thing. I'm not against VRV. Yes, VRV are good system, but provided you have right application for that. And also part load performance of VRV is good. So that means for a 10 ton of air conditioning, you will have to install probably 13 or 15 tons of air conditioning VRV system, so that then that system will operate at part load and will be efficient. So your first cost of VRV is also very high because you use more gas, you use copper, as well as little oversized system. But if you have variability in your loading, then still it would pay back. So minimum efficiency. See, here we are talking about central plant room efficiency. Somebody was asking me in the pre-lunch session. So this is where it will be. For a system less than say 100 TR, so your central plant room water cooled efficiency could be 0.21 kilowatt per kilowatt of refrigeration or 0.74 kilowatt per TR. And for the larger systems, it would be 0.2 and 0.7 kilowatt per TR. So when we say 0.7 or 0.74 kilowatt per TR, that means we talk about chiller power, then our cooling tower fan power, cooling water pump power, as well as our primary pump and secondary pump power. All these pumps will have to be efficient, so that collective efficiency. See, not long ago, even when screw chillers came into existence about 10-15 years back, a little more than that, still 15 years ago, we were used to say, yes, if we are able to achieve plant room efficiency of 1 kilowatt per TR, we are very good. But now when we talk about ECBC plus or super ECBC building, we talk about 0.74 or 0.7 kilowatt per TR, and then these are achievable numbers very easily. We have in fact retrofitted some systems with these kind of efficiencies. So here we get like a typical chiller data sheet. not about any manufacturer or something, but this thing. So cooling capacity is about 66 ton. So cooling efficiency is 5.02 COP, IPLV of 0.414 kilowatt per kilowatt, and temperature is 712, and the fluid flow rate across evaporator and condensers have been mentioned as 11.04 liter per second and 4.54 liter per second, and what would be a pressure drop across evaporator and condenser also. Then you have condensing entering water and leaving water temperature and condenser flow, and you have power kilowatt. So for a 66 kilowatt 66 TR machine, your maximum input power would be 46.1 kilowatt, so which is good. And then this is the value NPLV on part load value at constant entering condensing water temperature at various loading between 25, 50, 75 and 100%. And you can see efficiency of say anywhere between 75 to 50% loading, you will get a cooling water NPLV value of 0.431 to 0.552 kilowatt per TR, which is quite good. Or else in this system at constant condensing, your value would be of about 718 kilowatt per TR at constant condensing temperature at different loadings. Then you have piping duct work for ECBC, ECBC plus and super ECBC buildings, and these are the insulating R values. So even your quality of insulation and thickness of insulation also goes on increasing the moment you decide to upgrade your building from ECBC to ECBC plus or super ECBC building. So duct inside insulation or the flexible ducting for connections, as well as insulated duct from the outside. All these have certain U values. Piping joints in shoe bend also are required for minimizing the pressure drop from pump outlet to the header. If you join them at 90°, then there will be more resistance in this system. Then here in this system, there are no butterfly walls or non-return walls on the pump line. So that needs to be installed. It is again here you can see it's a direct T joint without shoe bend. So this is not so good engineering. So as a good engineering practice, you will have butterfly wall, non-return wall and bellows, expansion bellows for dampening the vibrations or isolating them. So balancing walls, everything would be provided. So system balancing is also there. So the construction document shall require all HVAC system to be balanced in according to generally accepted engineering standard. A written balance report including O&M guidelines to be provided. Achieve energy efficiency by optimizing air to water distribution rates for all systems. Air system balancing has to be there, as well as hadronic system, chilled water system by using impeller or trimming of impeller, installation of VFD should be there. Then condenser should have heat rejection clearances, and treated water for condensers need to be used. The cooling tower fills and the scales in condenser over period of time can cause heat transfer resistance or increase that, and then your cooling water system may not offer you the right size of air conditioning. So you have these cleaning mechanisms available which can be installed on the condenser tubes, which can then run through the system, create a turbulence and allow that turbulent water flow so that algae or scale or something does not go. Or you also have your this thing auto tube cleaning systems which are available. Then compliance to be demonstrated with requirements in 5.3.1 to 5.3.8 for serving which serves a single zone. Cooling if provided by unitary or package or split AC or heat pump unit. Heating again by unitary package or heat pump systems. And outside air is less than 1400 liter per second or 75% of the system. Then ECBC also talks about motor and fan efficiencies and pump efficiencies to be used in air conditioning system mainly. So for central systems and ductable VRVs, your minimum fan efficiency in ECBC building is 60% mechanical efficiency and minimum motor class is I2. And the return and exhaust fan should have a 55% efficiency, again motor of I2. But for ECBC plus building, the mechanical efficiency increases from 60 to 65% and from 55 to 60%, and motor efficiency is then I3. And in super ECBC building, the supply fan efficiency is 70% and exhaust fan is 65% and motor efficiency is I4. So all these efficiencies invested into a better design will also have a payback in, because your efficiency itself is going up. So if you look at this now, primary chilled water primary and secondary pumps in ECBC plus building, it should be 18.2 kilowatt per kilowatt of refrigeration or 64 watt per TR. Whereas in ECBC plus it would be 57 watt per TR, and in super ECBC it would be 52 watt per TR. Condenser water pump efficiency will be 62 watt per TR, 58 watt per TR, and 51.4 watt per TR. So pump efficiency will be minimum 70%, 75%, or 80%, 85% in super ECBC. So with all these pumps efficiency, chiller efficiency improvement, your super ECBC building is meant to consume at least 25 to 30% less energy as compared to ECBC rated building. Cooling towers are typically induced draft double flow cross flow cooling tower, where temperature range and approach are the parameters we need to be looked into, and how much nearest temperature you can get as compared to your coincident wet bulb temperature. Your cooling water system is the indicator of efficiency. So approach, the effectiveness of cooling tower is range upon range plus approach is the formula, and if you have good range as well as very less approach, then your effectiveness of cooling tower increases. So this is how typically a motor, fan blade and sprinkler assembly you can find. These are the fresh blue colored fills. Over a period of time they get added with this thing. Then fan with hub is how cooling tower fan is, and sprinkler with hub you can see. Cooling tower efficiency is also you will find in ECBC plus and super efficiency building. It will have VFD on cooling tower fans as well. And propeller and axial flow fans, you will have efficiency of 0.17 kilowatt per kilowatt of refrigerant or 0.31 kilowatt per liter per second of airflow. And if you have a higher capacity centrifugal fan, then the numbers would be again 0.034 kilowatt per kilowatt refrigeration and 0.59 kilowatt per liter per second. Air side economizer, again as I said, it can also have a 100% or partly modulating type damper and sensor if your ambient temperature goes during operating hours to a minimum level of say 16 to 14 degrees centigrade and below, and then it can allow to stop your chiller and AHUs etc., and only fan is run or only AHU is run. But provided if you have a separate ducting for providing such cool air even during night time, it can help you. Warm and humid zone is exempted from this because we will hardly have any significantly lower cooling hours where the ambient air temperature would be going below 14 or something. So project with only daytime occupancy in hot and dry climate are also exempted because it doesn't make any sense to have this system, because in the night it is not required. But in the night time, these hot and dry zone climate office buildings can be, or the areas can be pre-cooled in the night. So your morning peak cooling load can be reduced. and individual ceiling mounted systems of smaller capacity of 3.2 liter per second are also exempted. So partial cooling also can be provided by these cooling towers, and all air side economizers will be equipped with control that allow damper to be sequenced with the mechanical cooling equipment and not controlled only by mixed air temperature, and capable of automatically reducing outdoor air intake to the design minimum outlet air temperature. Then all these air side economizers shall be tested in the field for the appendix G for proper this thing operation. And variable flow hydronic system where chilled water and hot water shall be designed for variable flow to be capable of 50% of design flow rate, or minimum flow should be more than 30%. There will be provision for isolation walls on water cooled air conditioner or heat pumps for the pump motor larger than 3.7 or 5 HP motors, and walls to be interlocked with compressor to shut off condenser water flow when compressor is not operating. Variable speed drives to be put for all pump motors which are more than 5 HP or 3.7 kilowatt. And then for hot water generation boilers, especially in hospitals and guest rooms, we will have system efficiency of 80% to 83%. Then we have a heat recovery system. All systems of capacity greater than 2100 liter per second, or maybe 4500 CFM. The minimum outdoor air supply of 70% shall have air-to-air heat exchange recovery equipment. Then we talk about alternate cooling technologies, which is one is like radiant cooling. You have a structure cooling, but in structure cooling, you don't use chiller or chilled water, but use water at ambient temperature, and then try and maintain your slab temperature to a lower value so that you can achieve MRT of 32 degrees. See, here the technique is different, and this can very well be adopted in any building, even non-air conditioned buildings also. So it will help us in maintaining our MRT to a comfortable level. So acceptable MRT temperature for a naturally ventilated building is 32 degree or less, because our body temperature is 36.5. And if you have a delta T of 4 or 5 degree, then our body heat will be taken by the surface, or we will not lose our increase our body temperature from the surrounding, but in fact very gradually we will lose some amount of heat to the surrounding, which is acceptable. So to maintain this, you can have a cooling tower, closed loop cooling tower system. And if you run these kind of pipes on the slab, or you can insert them into a slab and then do the screeding and then do tiling or something, and then you run a small solar operated pump during daytime, it could be sufficient to maintain the surface. And this is how you can see this thing. So blue line is a slab top temperature, red line is a slab middle temperature, and green is a slab bottom temperature. So without structure cooling, slab middle and bottom temperatures are same. So in the night, slab top temperature reduces, but again during the daytime it goes up. But if you have a structure cooling, then your slab bottom temperature remains almost at 30 degrees centigrade constant. Some multiple trials were taken, and your slab middle temperature also then rises a little lower, because earlier it was touching or crossing more than 40 degrees centigrade in Mumbai, but now here you can see it is just about 37 or 38 degrees centigrade, and slab top temperature also is then much lower than that. So you will have much better uniform cooling at the bottom, which will radiate enough cooling to the occupants. Then radiant cooling itself, where ceiling suspended radiant panels, capillary system or slab cooling can be provided. This is a classic case of Infosys, very well documented, and many of you might be aware of this as well. So Infosys involving a lot of only IT people. So people are their machinery, you can say, on which they earn and do the company does the turnover. So they map KWH per employee per month as a one factor, their own way of this thing. So when you have a conventional design of air conditioning from their old offices, it was 53 kWh per employee per month. Then they changed to efficient design long back, and it came to about 29 kWh, so almost half. And when they did radiant cooling, their energy consumption went to 18 kWh per employee per month. That is 1/3 of the conventional air conditioning system. So this is the data, published data of theirs from between April 2011 to February 12. So almost 10 months data they have been able to publish, and it's a saving. So identical two wings of a building, one is with efficient cooling and one with radiant cooling. That is how they have created, and results are astonishing. Then chill beam systems are used, chilled water pipes in modular units and mounted to the ceilings, and then they transfer heat primarily through convection, and they are often used along with the dedicated outdoor air system DOS, where chilled water coil takes care of sensible cooling load and latent load will be taken or made by dedicated outdoor air system. So by decoupling sensible cooling from ventilation, you can have chilled water to be generated at two different temperatures, and it can give us the more control. So chilled beams use higher chilled water temperature of 13 to 17 degrees centigrade as compared to 4 to 7 degrees centigrade by conventional system. And thus the chiller dedicated for chilled beam cooling has a lower temperature lift and operate more efficiently. So kilowatt per TR of 1317 chilled water circuit temperature could be below 0.45 kilowatt per TR, which should, or even less than that, which should provide us a much better cooling. Then again, this is not possible in most part of Kerala, except for some island areas. But again, this is a good technique. So you have ambient temperature below 16 or 17 degrees centigrade, the chiller can be shut, or the chilled water temperature can be increased using only cooling water to be circulated indirectly, and then free cooling of primary chilled water loop to meet cooling load through the cooling tower itself can be done. And dedicated outdoor air system can be used for providing treated fresh air and positive pressure in the zone. Again, during winters in the composite and hot and dry climate, when ambient temperature goes below 20 degree, the free cooling can be employed. And even when in the night time offices are not used or something, those buildings can be pre-cooled so that you can avoid morning peak cooling load requirement, and you can have a very comfortable operating temperature. Direct, indirect, adiabatic two-stage evaporative cooling is also used. So a more refined version of old desert coolers with which will work well in composite and hot and dry climate, and where they will have more than 4,400 hours in a year where the wet bulb temperature will be less than 20 degrees centigrade. And indirect adiabatic two-stage evaporative cooling can also provide a controlled RH in the outlet as well as compared to uncontrolled RH being thrown by the old desert cooler system. So if you position your all AHUs on the periphery, then it can allow to take fresh air from the top or the side in every AHU room, and then it can provide by fan filtration unit, air can be supplied to the user areas, is how this system would work. Just another case, not again possible in major parts of the country because we have little higher pollution or the dust particles in the air, but In Europe, many such novel buildings are taking directly air from the outside when ambient temperature goes below a certain value in summer months. Their summer months, when temperature outside air temperature itself is 14 to 18 degrees centigrade, and they have automated sensors and dampers to take care of this system. This is again for dry climates and composite climates. Hybrid cooling issues can be done. So by rehumidification of purge air, it will enable indirect exchange of energy with ambient air to reduce heat load, and then using cooling water in winter and chilled water in summer and monsoon for sensible cooling of this air. Here you can see this is for the city of Pune, very this thing. So numbers, if you see, Pune summer ambient temperature is say 38.4 degrees centigrade, and dry bulb, and wet bulb is 20.52 degrees centigrade. RH is less than 20%, and if you see the absolute humidity, it is 0.0090 kg per kg is this thing, or the enthalpy is 61.677 kilojoule per kg. If you use the first stage of cooling, this rehumidification HU, what we saw in the previous slide, it will pre-cool that air from 38.4 to 27.67 in the first step. There is no heat gain here. If you can see, your absolute humidity will be still at 0.0090 kg per kg as a first step, but your enthalpy will come down from 61.77 to 50.81, and your humidity will kg per meter cube also will be little lower. Same way, then the next stage of heat exchanger, the temperature would drop down from 27.67 to 21.5. Your absolute humidity is still 0.0090, and your enthalpy is reduced from 50.81 to 44.52. In the third stage of indirect cooling, temperature drops down to 19 degree. Your enthalpy is still same 0.0090. This thing, and water vapor humidity content is also same. And then if finally you apply some evaporative cooling, where your supplier temperature drops to 15.3, and your enthalpy again reduced, slightly increases to 42.14, and your RH goes up. And then now either you can choose to pass this air through your system, or then maybe run a chilled water coil if required for a very small quantity, so that that pressure temperature would drop from 15.31 to about 14 degrees or so. So this is still possible. So your 38.4 degree temperature and 20% RH, you can indirectly this thing, by using indirect and evaporative cooling, you can take it to almost 89.9% RH and 15 degree of temperature. Also, if you have variable speed turbomagnetic chillers and screw with variable speed control or constant speed, here you can see at various percentage loading, your magnetic levitation chiller COP goes up very high, and that is where you will save a lot of energy. Then combined effect of variable temperature, so variable speed with change in evaporator and condensing temperature, if you manage that with operation and controls, then for a dry and relatively mild climate winter, we can have a good saving. And this is how a chilled water variation temperature, if you can see, your chilled water temperature can be increased to 1319, and your cooling water condenser inlet outlet temperature can be managed between 29 and 35, versus 612 generation and 2935, versus constant speed 612 chilled water generation and 2834 cooling water temperature. So your COP of 18 also you can get at part load of about 50% loading. So this kind of changes in this chiller set point and managing your cooling water set points will also provide us enough energy conservation opportunities. This is the solar air conditioning system. Again, as an alternative cooling we had installed. We talked about this in the morning. So this is 160 tons of air conditioning in a municipal hospital, And here what we have clubbed is you get 184 number of parabolic solar concentrators are there. They generate steam at about 6 bar, which goes to a VAM. Then there is a cooling tower for rejecting that heat. And then that chilled water goes to the OPD and other hospital areas and come back. Then that condensate is again taken back to your solar concentrator for the steam generation. And in addition to that, we have employed a liquid desiccant dehumidification system, which is unique and can be very useful to coastal areas like ours, where a incoming air is dehumidified using a liquid desiccant, and then that air at sorry, hot air at about 6 excuse me, that hot air is cooled you indirectly using a normal chilled water temperature, and then that air is given to OPD waiting area as a once through system. This is how this system has been functional for almost like 13-14 years now without any fossil fuel based or electricity based chiller operation. These are the solar parabolas. This is the liquid desiccant dehumidification system. Then you have BMS, where climate, building operations, then systems, all that can have passive measures, active measures, and control mechanism, renewable energy. All these logic, they can help you to monitor performance of microclimate or indoor air quality, thermal comfort, visual comfort, water energy management, and safety, all these things. So BMS can then be used to make this data. And last is geothermal, again not to be employed this thing, maybe Dehradun, Chandigarh and above areas can use this, where there is a significant amount of temperature between summer and winters. Winters are very harsh, summer. So if you allow that air to be taken 4 meter below the air, this thing, then it can use that building for heating as well as cooling system. So in winter, summer heat stored by the infinite soil around that building can heat up the cool air, and that building can be heated. Or in the winter months, so always you will get one season behind room conditions by using geothermal energy. You may and you may not use refrigerant flow in that circuit as well. So emissions are 70% less than the conventional system, and good amount of heating energy saving. So if you are in the northern parts of country, Dehradun, Shimla or Manali or above, then these kind of systems would work. Then I'll just run through something which always is talked as an energy modeling requirement in the ECBC. So at the pre-design or conceptual design stage, owner, architect, and energy modeler or HVAC consultant would have multiple meetings, understanding of situation, and a preliminary design would work by the architect and energy modeling agency. Then that data is analyzed and shared with MEP consultants for system configuration. And then that energy modeling agency would come into picture again and do the iterations of the various proposed energy conservation measures. Then these are discussed with the owners and cost benefit analysis is done. And once they approve something, then final design it gets incorporated, and then it can be weighted by ECBC compliance by the EC cell at the ULB or the state nodal agency. So at a pre-design phase, preliminary energy modeling based on the conceptual design is done. Evaluation and recommendations for the best building orientation, harvesting daylight, minimizing solar heat gains, etc. are done. Then various factors considering while modeling are the climate configuration, orientation, location, thermal properties of construction materials, wall, roof insulation, are done. And then at the design phase, daylight strategy, shading devices, then baseline conditions of ISO 90.1 ECBC are incorporated. Then building simulations are carried out for varying compliances, and then based on the techno-commercial analysis, energy conservation measures which can get incorporated are added to the building, and the sequence of conservation is also then taken care. So it can test the building before even it is being built. That is the best advantage. And the design energy cost to the energy budget cost of a building can be used. So it for heat balance in the building, material data, design data, building usage data, climatic data, etc. are being simultaneously used. It is used for determining cooling and heating loads by mathematically simulating the thermal performance of a building. Design energy use for a course of a year by mathematical simulation is done, and operating hours data is fed to arrive at cost. It is necessary to test the building before it is built for is the increased productivity, less absenteeism, that is the benefits. Then energy efficiency, cost effectiveness, most measures have less than 5 years payback, so which is good. And environmental benefits like commitment to global warming, reduction of solar carbon footprint, as well as depending on the renewable sources, and get a sustainable or green design. You can have your building cooling load, the peak demand and its profile, building energy performance analysis, building energy management and control system design, building regulation code standards, compliance checking, performance contracting, utility cost analysis, passive design feature study, lighting, daylighting studies, and CFD analysis for any naturally or mechanically ventilated spaces. The steps are typically identify your objectives, you create a thermal zoning plan, operation scheduling, internal loads, construction materials and assemblies, define space and zones, defines HVAC system and utility rate. When you select the software for simulation, you need to check its capability and flexibility, then accuracy, processing time. It should not take like 1 week to do an iteration. Yes, there are some softwares which take that much time, but then that is not required. You probably need a quicker answer which could be reliable. Then user input data preparation. If it is too lengthy to prepare so much of data input even at a schematic design or conceptual design stage, then that won't help. Then how much documentation or outputs you can get, reliability, validation, and user support, which is most important. So in case you get stuck, who is going to help you? Then lighting, envelope, ventilation equipment, and people loads are there. See, typically lighting, you can have a great controls like motion sensor, daylight sensors, etc. Envelope also is once built, it can give you a great control over what you design. Ventilation equipment, usage pattern, you don't have this thing, and occupants, you have practically no control because they will keep moving as per their job requirement or from one department to other or within the section as well. So you will have to live with some limitations on that. So these are the internal and external loads of conduction, convection, radiation from machines you will have. Then you will create these kind of occupancy schedules for weekdays, Saturdays, Sundays, holidays, etc. So which equipment, which lighting, and which occupancy will happen on those days. Then kind of lighting and daylighting quality analysis you can do this. And now we will come to a case study of one Aranya Bhavan building in Jaipur using ECBC and design charrette techniques. So in December 2012, this design charrette was conducted for the Rajasthan Forest Department building Aranya Bhavan, and the building contracting agency was the Rajasthan State Road Development Construction Corporation, again a government, the state government, this thing. And the architects were the local team from Jaipur. Then construction and technical support through a building energy efficiency project of Indo-Swiss BIP project was shared. And in March 2015, building was inaugurated. And then in 2015-16, we did the extensive long-term energy monitoring in summer and winter. So Jaipur, as you can see, is though in Rajasthan it is covered as a composite climate and not the hot and dry climate as part of the other parts of the Rajasthan. Surrounding of the building, you can see there is not much of vegetation as well as bare small hills. This is little on outskirts of Jaipur towards the NH8 bypass to Delhi. Before Shared, this was the plan, three wings connected by two stairwells in now position. And this was a model view of building, a 3D view which was created. A building actually looking like typical Rajasthani culture or something. And the goal for this kind of design Shared to evaluate was to have an EPI of 90 kWh per meter square per annum or better, and also to demonstrate ECBC compliance to that building. And after 3 days of charade, the EPI goal was reduced to 77 kWh per meter square per annum. And then the second goal was to be better by at least 20% better than ECBC. So this was the challenge taken up by the design team. The walls were normal 230 mm brick wall with 2.05 watt per meter square degree Kelvin U value. Roof was 150 mm RCC slab, 3.2 watt per meter square degree Kelvin U value. Glazing was single 5 mm clear glass, and air conditioning VRV system was used, and there was no STP or something was considered as a part of design. Then firstly, daylight analysis area was done for this highlighted area in the red, where chief conservator of forest office with his PA rooms and antechambers and toilets etc. was done. And it was seen that there was no light in these spaces of PA rooms. Both these PA rooms were not getting any daylight, and the veranda reduces daylight availability to the depth of veranda can be reduced, and certain daylight simulations were carried out. And now you can see the revised this thing. So toilet area was this thing. So the shaft size was increased and some windows were added to the PA rooms so that there would be some direct light would come inside. And toilet size were little compressed from 2.5 meter width to 1.7 meter width, and that provided some windows to other areas. Then a whole building performance method was carried out for the annual simulation for this building. So ECBC prescriptive approach was compared with the proposed design. So opaque wall, outside wall was used with space insulation. Then roof was kept almost as it is. Then glass was changed from with proper shading and DGU, and centralized air conditioning system was provided with chilled water instead of a VRV system. This is during construction this building looks like. So in the here you can see when 1.5 inch insulation is being used, or 2 inch insulation being used, sandwich between the normal brick walls at the construction stage. So roof was insulated with a high solar reflective index material. This is the wall insulation, and the glaze area was reduced, and this is how the completed building looks like. Actually, amount of window to wall ratio than the original design, it has been reduced, but inside you get still nice light due to simulation done. And the building also does not look like an ordinary building, look like a haveli or a palace in similar thing to Rajasthan buildings. This is the backside of the building, connecting stairwells. This is inside the main entrance. You can see amount of light coming. Stairwells are very well connected. On the top, however, they didn't change it to the glass or something, and polycarbonate sheets were done. So in the summer, the polycarbonate sheet was getting heated up to 54.8 degrees centigrade, and that was very high temperature. Lighting were all T5 and LED lamps, and very good LPD of 0.53 watt per square feet was there. Then STP was installed, chilled water based cooling system was done. HVAC was 3 numbers, 110 TR, three chillers were installed, two operating, one standby. This is what exactly we talked about the reduction in cooling in the morning. I had showed you this slide. So we achieved about 28% reduction in the building, and these were the all other cooling tower and system. So we installed these cooling towers, and for that cooling tower, we installed an STP, and treated water from STP goes to cooling tower. On the building rooftop, 45 kilowatt solar PV plant was installed. Additionally, for their guest rooms, solar hot water system were installed. It generated about 60,000 units per year. Outdoor lighting was done with LEDs. Inside water cassette and split units were installed. Basement ventilation was done, and the building was inaugurated in March 2015. The built area of less than 10,000 square meter, G+4 building with one semi-basement for parking and services, and about 350 users, offices, museum, library, auditorium, and couple of guest rooms are there. So again, we reduce the demand through passive measures, use efficient system with controls, and then integrated renewable energy system. Post occupancy in summer and winter, 15 days long-term monitoring with multiple data loggers was done by us to monitor actual performance of all panels, everything, and a lot of data was collected on site. And this is post occupancy this thing. So you can see from November to February, there is no cooling load because they don't need that. Temperature drops down, and so building still remains comfortable during these months. And chiller performance, as I mentioned, for a whole system, it was 0.485 kilowatt per TR is what they are getting in terms of kilowatt per TR value, always below 0.5, which is possible. So this building, even if we see 2016 ECBC or new ECBC, it is still better than that in terms of super ECBC. Plant room performance is also below 1 entirely. Chiller, pump, cooling tower, everything. So summer and winter monitoring on energy consumption gave us some insights about what can be done. Still, we could identify some energy efficiency measures in this high performance building as well by improving approach, reducing contract demand, by operating better pumps or something. So all that had saving potential of or payback of just around 1 year for the investment. Then another thing was done. We had simulated energy performance index prior to this thing, and then we did the actual measurement on the electricity bill. So for certain months that EPI was higher and lower, but overall building did very well then as compared to expectation. So actual EPI was 43 kWh per meter square per annum, where the goal was to reduce it below 70 kWh per meter square per annum. And BEE 5-star benchmark is for composite climate is 90 kWh per meter square per annum, which this building is half of that. Then again, we did the calibrated simulation and recreated this building in the simulation software and applied. And we compared the ECBC prescriptive approach simulated with proposed simulation and actual measurements. And with addition of 60,000 units, this thing from solar PV, there is a significant amount of reduction. So EPI before Sharet simulated what we claimed from 90 to 77, and then after completion it was simulated to be 53, but actually building achieved EPI of 43. kWh per meter square per annum. Cost of construction earlier this thing budgeted was 30 crores. There was an increase of 60 lakh units, but with annual energy savings of 3,40,000 units and solar generation, payback is hardly 1.5 years. So it is a BEE 5-star rated building. Thank you.
Thank you, sir.
Mithun. Yeah, Mithun, I see now one question. How often should a condenser evaporator tubes clean, considering clean RO water enters the system? If you are using RO water, once in a year should be good enough, or may not be. Means once in a year should be still very good number. But if you use auto tube cleaning system, see, because using RO water, another 50% of water you are ejecting, right? So what you do with that water? So by using RO, you are also polluting that water and balance. High concentrated water is rejected, and where do you store that or throw that? So RO maybe using in once in the evaporator circuit, chilled water circuit is good, but for cooling tower, using RO is criminal actually. Please enlighten us on chilled water thermal storage, energy storage, and ice water energy storage. See, these two systems of chilled water storage as a hot well, cold well, or using ice bank system, they're very old technologies. And if you have a time of the day tariff in your state, where state electricity board or utility penalizes you for peak morning and peak evening hour usage and offer you incentive for nighttime usage, then you can have this system generated. Because if you want to generate ice, then you will have to or use this thing glycol MGL based system. Then that for generating that glycol, you will have to generate a system this thing, and your kilowatt per TR would be close to 0.9 kilowatt per TR or so, because you will be generating that ice at sub-zero temperatures. So your efficiency of chiller will go down, but then it has to be compensated by the morning and evening peak usage tariff. On the other hand, if you have a chilled water based system as a storage, hot well, cold well system, then again you can either generate that chilled water in the night hours and use during the day, because say in Maharashtra, all utilities do not record maximum demand during night hours, so you can even exceed your contract demand. And when you pay 400 rupees per kVA or 500 rupees per kVA as demand charges, so if you can have an ample storage and place for that, then during daytime only you will have to run your AHU and secondary chilled water pump. So you can substantially reduce your building demand. So that is one benefit you can have. And nighttime tariff also, it should be lower. In Maharashtra, you get 80%, almost 80 paisa per unit rebate. But in the evening tariff is 1 rupee 20 paisa, and morning tariff is about again 1 rupee they charge. So anytime if you are generating between 10 to 6 during the daytime, it is a base rate. In the night time, you get 80 paisa rebate. So if these systems or these kind of TOD tariffs are available in Kerala, in your state or any other state where you are working, then it should be good system to install, provided you have place. And also for glycol chiller, you will need to also maintain, because glycol as a brine is also little corrosive. So you need to do periodic testing of that brine, as well as you need to clean plated exchangers. Otherwise, what happens if you don't clean plated exchanger, then entire corrosion gets coated on the plated exchanger sheet, and your heat transfer area suffers. So, but yes, we have done these couple of projects for providing reliability to some data centers as well as for building where they have gain, and in less than 4 years they got their money back as well. We converted a couple of their extra chillers which were lying there to these this thing to a glycol based system and use that. So this is it. Anything else you need to know?
Participants, you can unmute yourself and ask any question.
Thank you, sir. I think there are no questions from participant side. Participants,
Okay.
please fill the feedback form. The link for the feedback form is given in the chat box. The same will be sent to you by mail also. Kindly fill it. Thank you, sir. Thank you for the well organized and informative session.
Okay, thanks a lot. Rena, you can share my name and email ID with these participants. So if they wish to
Okay.
contact, yeah,
Yes, sir. I can show.
or even I can write. Thanks a lot. Thanks for patiently listening. Bye.
Thank you, sir.
Thanks.